Let's get started. Good afternoon, everybody. Welcome to exciting afternoon of organic chemistry, Chem 170, with your host, me, Dr. White. All right, we got a lot to do. One of the things I was checking earlier today was the date I had for test number 1. And I've done this in past semesters. Because we started late, I lost 3 hours that Wednesday that I would have been lecturing. I might move. We'll see where we get by the end of this week. Test number 1 a week later. That way you'll have more time to study and you'll do good, excuse me, oh, an itch in my eye, on test number 1. Now, some friendly advice. Historically, and it usually is always true, test number 1 has the highest average. It's the easiest. Therefore, you should be studying now as hard as possible. You should study all the time, but especially now to get the most points on test number 1 because it's the easiest. Now, students have recovered if they didn't do good on test number 1 and got good grades. But if you get good score on test number 1, that makes your life easier. I don't know about you, but I like to make my life easier. I hope you do. All right. On last Wednesday, I talked about where you find certain alkanes, like, let me do this. An example would be natural gas. This one I think you might be familiar with. These are all alkanes. Did I ever tell you I'm always the first one down in spelling bee? Math and science, I'd win. Spelling was never my cup of tea or anything of math. All right. Barbecue propane. Gasoline contains alkanes, and baby oil contains alkanes. It's mainly alkanes. So is petroleum jelly, which you know as Vaseline. And then paraffin wax, which is 50% of good candles. Which reminds me of a quick story. When I used to work for this Anglo-Dutch company, I used to spend a lot of time, because they were headquartered in there, in the Dutch city. Now, Americans pronounce that Gouda, where the cheese is from. The G in Dutch, the Netherlands, Dutch language, is not pronounced like an American G. The name of the city is really Gouda. And Gouda, when I went there, besides great cheese shops, and they do have some great cheese shops, they also had, they're renowned or known for hand-dipped candles, which I have a collection of them. I don't think I'll ever burn them. They're too beautiful. All right, so on a test, if I were to ask you, give an example, 3 points of an alkane in your daily life, you could say propane for your barbecue, gasoline, baby oil, Vaseline, paraffin wax, or even natural gas. Did anybody happen to drive by a gas station and think of, oh, they're selling alkanes? I got the whole semester to work on you because when you leave my class, you can think about organic chemistry. And I promise it won't hurt, guaranteed. Because organic chemistry is everywhere. I stole that from SpongeBob. But anyways, think about it. And guess what time it is? It's new functional group, new chapter time. It's time to move into chapter 3. But first, a commercial from me, Dr. White. That is on Wednesday. I will go through the chapter 2 alkanes problem set. You don't have to hand anything in, but if you want to get a good grade, I highly recommend you try it before I go through it, because practice makes perfect, meaning you'll get a good grade on test number 1. And also after test number 1, you'll find out why I call them practice problems. Hint. So let's look at the new chapter. And this new chapter is called alkenes and alkynes. Remember, you learned about alkanes, A-N-E-N ending, and now this has an E-N-E ending, alkene, and also another functional group, alkynes, which has a Y-N-E ending. So what's an alkene? Well, it's a hydrocarbon. Remember, hydrocarbons are molecules that contain only carbon and hydrogen atoms, and this also contains a carbon-carbon double bond. And I will never ask, but sometimes they ask on entrance exams, or certain exams, I will never ask it. If you have an alkene with 5 carbons, how many hydrogen? Here's the formula to calculate that. For my class, you don't have to know that. Now, the way we show an alkene, a double bond, is a carbon with 2 lines. Each line is a pair of electrons. Therefore, you're sharing 2 pairs of electrons between these 2 carbon atoms, and that's a double bond. Now, hopefully you learned about single, double, and triple bonds in your general chemistry class. Now, an alkyne, remember this is Y on the ending, is a hydrocarbon, a molecule that contains carbon and hydrogen, that's a hydrocarbon, and contains a carbon-carbon triple bond. And a triple bond we show by 3 lines. And that's 3 pairs. Each line is a pair of electrons. They're being shared. Same thing up here, 2 pair of electrons shared. So you have an alkene, E-N-E ending, which is a double bond, and then alkyne, Y-N-E ending in the name, and you'll see that in a little while today, is a triple bond. Now, here's the formula for a triple bond. I'll never ask that. This is called the empirical formula, which most of the time in organic chemistry is not that useful, which is why I never asked that on a test. Yes, I know it, but I'm an organic chemist. I should know that. Now, these are called unsaturated hydrocarbons. And I'll never ask you on a test what's an unsaturated hydrocarbon, but that's a hydrocarbon that contains less hydrogen atoms than an alkane, which is considered a saturated hydrocarbon. And hydrocarbons that contain one or more carbon-carbon double or triple bonds are unsaturated. And I'll teach you later that the addition of hydrogen gas, H2, will convert an alkene or an alkyne into alkane. And these are things I will never ask on a test, but I will discuss this. Now, how many of you have heard of unsaturated fats? And I'll teach you later in the semester when we get into that. We're going to get into a lot of neat stuff in this course. I can do that because I'm an organic chemist who's worked in the real world. That makes it fun. And that means you have a fat or oil that has a carbon-carbon double bond or more than one. Mother Nature never did triple bonds. Only organic chemists did that. So you'll never see an unsaturated molecule that Mother Nature made a triple bond. Now, I should have taken this slide off, just ignore. Sorry. I used to talk about this and it doesn't make sense in this course. Now, before we go into nomenclature, the next number of weeks, when I introduce you to new functional group or functional groups, I'm going to do a similar pattern. One, I'll introduce you to it. Hello, here's a double bond. Uh-oh, that was bad. But anyways, and a triple bond. Next, depending on the order, I'll show you where you find these things in real life, because that's what makes organic chemistry interesting. All the stuff I'm teaching you is in your daily life, because my world of organic chemistry is your world of organic chemistry. You just don't know about it yet, or you'll be learning about it this semester. And then I'll talk about nomenclature. Remember, nomenclature is the fancy word, how to name things. Then I'll talk about how do you make one. This first functional group I won't, because you need other functional groups, and I'll teach you those later. And then the fun part, how they react. That's really fun to synthetic organic chemists, because that's how you can make new things that are used for your daily life. So let's look at some uses of double bonds. Now, I'm going to assume, and correct me if I'm wrong, that each and every one of you at some time in your life up to this point has seen a carrot. I should have brought one from the refrigerator. Bad, Dr. White. And you know what color a carrot looks like. And you know why a carrot is that carrot color, orange? Because of this molecule, beta carotene. Now, you don't have to learn the structure of beta carotene, excuse me. And every bend in a line is a carbon, every end in a line is a carbon. And you see right here, the two lines between two intersections or bends, that's a double bond. And this has a lot of carbons, and this has a lot of double bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 double bonds. And this is called beta carotene. And beta carotene is responsible, the molecule responsible for making a carrot look orange. Now, how does it do that? It's really beyond the scope of this course, but I'll just briefly mention double bonds that are alternating. Notice double, single, and so on. It's called conjugated. I won't ask that on a test. They have the ability to absorb different types of light. And for beta carotene, the light you see in your room or from the sun has all different colors mixed up together. You know, the colors of the rainbow. What was that in high school? Roy G. Biv. Remember red, green, blue, and everything else? But anyways, this molecule absorbs all the colors of the light except the ones that form the color orange. And that's how the carrots get their color. Now, how many of you have heard that carrots are good for your vision? And one of the reasons why they say that, and I'm not sure how good it is or how many carrots, but I try and get my carrots. I like carrots. And if you remember, Bugs Bunny had good vision because he ate a lot of carrots. Why? Because your body breaks down beta carotene to new molecule, and that's called retinol. That's a retinal, I'm sorry. And that's the molecule that helps your eyesight. Retinol. And that's why they say carrots are good for your eyesight. By the way, I'm still grateful, and I'll see them Thursday to see if I actually need a prescription. Last November, I had double cataract surgery. It's hereditary. It has nothing to do with my retina or carrots, and I don't need glasses anymore. I hope. All right, let's look at another molecule. Now let me get personal again. I'm going to assume all of you have seen a tomato. And the red color of a tomato, as you see there, is due to this molecule. And this is similar, but not the same as beta carotene. This has got a common name. Beta carotene is also a common name. Later on, I'll teach you the difference between IUPAC and common names. And this is called lycopene. And this is formed in the skin of a tomato to give it that red color. Now, what this does in your body, I have no idea. I'm not a medical doctor. I'm a PhD in organic chemistry. So I understand there are double bonds here, but why that makes it, how that helps you or helps the tomato, I have no idea. Someday when I got nothing better to do, I'll look that up. Now, there's one more chemical I like to talk about. How many of you ever bought anything and it says on the package, new lemony, fresh smell, or new citrus smell? And you wonder, how did they do that? Well, they put in a molecule that's found in the skin of citrus, and they can also make in chemical plants, but I think now it's cheaper to get it from the skins of citrus fruit that are byproduct. And limonene has this structure. Now, this is the sixth structure you find on the internet. Every end of the line, there's a methyl group here. Oh, it's a six-membered ring. You see, you have a double bond here. Now, this dashed line we use in a wedge for stereochemistry tells this group at the bottom is underneath the ring, which I don't teach stereochemistry that much in this class. And you got a double bond here outside the ring. And this is a molecule that gives things that lemony, fresh, or citrus smell to it. And if you buy a number of cleaning products, you go, lemony fresh, that must be good stuff. Guess what? most of that is just put in to make you think, oh, this is good stuff and it smells good. I'm going to buy it. And they do that a lot in a number of things you buy. All right, let's talk about nomenclature. Now, nomenclature is how you name something. So let's do double bonds. Double bond alkene. And let's put one up on this whiteboard. By the way, I hope you've all started learning hint, the alkane 1 through 10 names, and the alkyl groups I gave you. Now, remember, there's 4 bonds to carbon. So if we look at this carbon, how come there's only 1 hydrogen? Well, there's 1 bond here, and there are 2 there. 1 plus 2 is 3. 4 minus 3 is 1 hydrogen. Now, if we look at this carbon, it has 2 bonds to it, but it should have 4. 4 minus 2 is why we have 2 hydrogens. So remember, there's always 4 bonds to carbon, and a double bond counts as 2 bonds to that carbon. That's why we have 2 lines. Now, how do you name this? Well, good question. Thank you. The ending ENE is used to designate a carbon-carbon double bond. Now, I'm not going to end this class, and this you can delete right here. First of all, just like alkanes, find the longest chain, carbon chain, and this is important now. That includes both carbons of the double bond. We'll come back later and do triple bonds. So just like an alkane, A-N-E ending, you find the longest chain of carbons, but now it's important that that longest chain includes both carbons of your, in this case, double bond. Then what I don't have here, oops, I'm missing something, so I better talk about it. Sorry, actually the one where I just named it, I guess, select the longest, and I should say, and now I'll show you what to do. Let's go back to our example. Now, we have a double bond, and how many carbons? Well, there's only one chain, 4, and that's butane. But this is not butane, it's a double bond, an alkene. And what you do is you erase the A-N-E ending at the end of the chain or the name, the alkane name, and you add E-N-E ending. E-N-E ending is a double bond. So that's butene. But now where is the double bond? And you count from either end of the chain to give the lead carbon the lowest number. And here, this would be 1. So we name this 1-butene. If it was 1 over, it would be 2-butene. And that's how you do it. So let me go through it again. You look from now on, and this is something we'll be doing the whole semester. When you look at an organic molecule, look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen atom. That's where the fun is. And that's where the functional group is. So immediately I see a double bond as an alkene. How do we name it? Find the longest chain. 1, 2, 3, 4. Name it butane. Drop the ane ending and replace it with ene. Remember, ene is double bond ending. And then you need a number. Which carbon is closest to the end of the chain? That's given the lowest number. In this case, it's 1. Now, if you have alkyl groups, you handle those just the same way as you've done in the past. And let's do an example. Now, in nomenclature, functional group carbons have higher priority than substituents, alkyl groups. Therefore, they always get the lowest number. And now if you look at that molecule, do you see something like a red flashing light saying, I'm different? And the answer is yes, a double bond. So this is an alkene. And I'm going to let you figure out how many carbons are in the longest chain. I'm going to let you have some fun too. I just remembered I forgot to add the poll question. Let's see something. Oops, hold on 1 second. Let's try to see if this works now. All right. And this is anonymous. So go ahead, click on one of those. Oh, I got to launch it. I'm sorry. All right, let's see if it works. And the votes are coming in. And it looks like everybody's done. So let me get to work. And we'll be using that when I do certain problems. So the longest chain is 1, 2, 3, 4, 5, or this could have been 5 too. That's pentane. I'm going to drop the ane ending. And since I have a double bond, not to be confused with James Bond. Oh, that was awful. Sorry. But anyways, by the way, Sean Connery was the best James Bond. But anyways, add ene engine, pentane. Now, what's the carbon of the double bond that's close to the end? And the answer is 1. So it's 1 pentane. Are we done? No, because as soon as I say 1 pentane, that's all spoken for. And look what we have. It's your old friend, the methyl group. And what carbon is it on? Well, we've already said this is 1. Therefore, it's on carbon 4. And this is 4-methyl-1-pentene. Again, find the longest chain. We did 5 carbons. That includes both carbons of a double bond. That's always important. and name it as an alkane, 5 carbons pentane. Drop the ane ending and replace it with ene ending, which we did right here. Then what carbon double bond is closest to the end of the chain? 1. And then the alkyl groups we name, CH3 is methyl, and it's on carbon 4. And that's how you do it. Oh, I better share. And there you go. Have fun. If you can, turn on your webcams this way I can see real faces. That makes me happy. And for those of you who have turned it on, thank you. And let's try this again. And it looks like everybody's done, so I better get to work. When you look at this molecule, you look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen atom. And look, it's a double bond. That's just like a red and blue light in my rear view mirror, fire truck or whatever. I got my attention, double bond. How many carbons in the longest chain? Well, let's count. 1, 2, 3, 4, 5, 6, 7. Remember, you have to have both carbons in double bond, and that's heptane, ane ending, if it was an alkane. But it's a double bond, heptene, because you have a double bond that has an ene ending. What's the carbon closest to the end? Right here. So that's 1 heptene. And that's how you do it. Oh, let's do one more. Practice is good for your grade. I'm sure you all would like that. And did I tell you about the 20-second rule? Before you write down what I write down, give me 20 seconds in case I change my mind, because I'm doing this. Once I start putting hydrogens, you know, I'm done in terms of changing my mind. Once in a rare moon I do, but most of the time I don't. when I'm doing examples, I do it on the fly. What would be a good example? And the question is, give the IUPAC name for the following molecule. And I have to apologize once in a while. And the answer is no, they don't always start with number one. You'll see later on why I'm doing this right now with them at number one. But the answer is no. And James, thank you for your question. All questions are good questions. Did I tell you how great IUPAC was coming up with the rules? Any molecule, if you do it correctly, only has one IUPAC name. Again, any molecule, if you do it correctly, only has one IUPAC name. And to come up with those rules, IUPAC did a beautiful job, amazing job. I think everybody's done. So let's do this. Now you look at B and you look at that molecule and look for what's different. What's not a carbon-carbon single bond or carbon-carbon or carbon or hydrogen atom should get your attention like that. And if I look at, ooh, a double bond, it got my attention. And realistically, when I look at an organic molecule, what I'm training you to do is look for what's different. Another way of saying that is look for functional groups, because that's where all the fun and action is. That's a double bond. How many carbons in the longest chain? 1, 2, 3, 4, 5, 6. I go 7, 8, but this goes 7, 8, 9. Remember, you have to have both carbons of the double bond, the longest chain. And hopefully you all agree 9 is greater than 8. And an alkane with 9 carbons is nonane. Drop the A-N-E ending, N-O-N-A-N-E, I did, and it's a double bond. I think I need a new tip on my stylus. Well, I should practice my writing on here again. And that's nonene. Now, notice the carbon of the double bond close to the end is 1. And then are we done? No, because this is all spoken for now, 1 nonene. But we have 2 carbons, and that's ethyl. And what carbon is the ethyl group on? Carbon 6. So this is 6 ethyl, 1 nonene. And that's how you do IUPAC names. Now I'll come back to the other question about nomenclature in a little while. And there's a reason you'll see in a little while why I've done all these with the double bond position 1. Now we did number the carbon chain from the end nearest to the multiple bond. This is true for both double and triple bonds. So that carbon atoms have the lowest possible number, indicate the position using the lower number. We did that. Now I'm not going to do in this class if more than 1 double bond is present. And we've already done number 6, alkyl substituents, alkyl groups, are named the number similar to the alkanes. So we'll come back to this, but we did some practice. Now, not so much in alkenes and alkynes, but later on other functional groups, common names are widely used instead of IUPAC names. And where are you going to see those? Well, on ingredients labels of stuff you buy, which is why I'm going to teach you that. Now, there's certain common names I'd like you to know. On a test, I'll never ask you what's the common name of this structure, but I will ask you to draw the structure from a common name. So if you're looking at a label of something you're about to buy, the ingredients label, and that name is there, you can say, oh, I know what that is, and it'll make you feel good. Now, ethylene, which is really ethene, is this molecule. This you don't have to know, because it's not that widely used in your daily life, ethylene, but it's used to make other things. And this molecule, one of the uses is to make the food wrap, otherwise brand name saran wrap is made from ethylene. Other things in your daily life. Now, another one is propylene. And these are common names, organic chemists. Shouldn't be a 2 there. And propylene, which propene would be the correct name, but nobody uses that. Have you ever bought something that's small thing that's in that plastic blister package? Like small, like a thumb drive or a little electronics or other things. And then you try and open it up. You try scissors and everything else. You're ready to blow it up because it's so tough. That material is made from propylene. It's called polypropylene. Now, the one I will ask you to know is acetylene. And acetylene is the simplest triple bond we'll talk about later, triple bonds. I can either draw it this way or I can draw it this way. And how many of you have ever seen on TV or in the movies, or if you've gone to a body shop where they have this real hot torch, you know, and you see this real hot flame coming out and they're holding it and it can melt metal. And if you see, I don't know if it's true or not, where you see in the movies where they're trying to cut the combination lock out of a big heavy vault, they use that. Those are called acetylene torches. And a acetylene torch is oxygen with acetylene. And because of the triple bond, it burns at a lot higher temperature than methane, natural gas, or propane, which is your barbecue, which those two will not melt metal. This will when it reacts with oxygen, I'm sorry. Let's do something. Never done this before. Let's see if you can all see it. I'm teaching myself something. Methane in Fahrenheit, 3,500. Propane, 5,000. Acetylene, 5,600. So propane's pretty hot, but this acetylene is much hotter. And on a test, I can draw the structure of, and I can put down acetylene, and this is the structure as you should know. This is called, on this carbon, right justified hydrogen, I'll never ask. And this carbon, it's left justified. When you have a carbon all the way at the left of a structure, you can have either of those. The rest of the structures are always right justified. So that's acetylene. All right. Now there's one other common name that I won't ask you to learn, but it's in our daily life, and that's a vinyl group. A vinyl group is a substituent that has two carbons and a double bond, and it's bonded to something else. How many of you have ever heard of vinyl floors? I think a lot of you might have. And that's made with molecules that contain a vinyl group. All right, next couple of slides on click the switch. Will this be on a test to partially off? A few things I might ask you to learn, other things I just want to cover, but I'll tell you click if it's off or not. That means it will never be on my test. Speaking about tests, quick commercial from Dr. White. Don't forget, I have my office hour tonight from 5 till 6:15. Different Zoom login. It's in the syllabus. It's also on the front page of the first page of Chem 170 and D2L. If you have questions, stop by. I'll be there. All right, now, when we talk about a double bond and a triple bond, the two lines are two bonds, but they're not equal. One is called the pi bond, the Greek symbol letter pi. The other is a sigma bond, and you should know this. So double bond has a pi bond and a sigma bond. And like I said, it's abbreviated by the Greek letter pi. Now, the next thing, this right here, you don't have to know, and it has what's called 3 hybridized sp2 orbital bonds, and that's where 3 electrons carbon has to share, and the fourth one is what we call p orbital. Again, you don't have to know that, and the bond angles of a double bond are 120 degrees. Again, that won't be on it. Now, because of the pi bond, there's no free rotation around the carbon double bond due to p orbital overlap of the pi bond. This will never be on a test, but it's something important so you understand an important thing about double bond. All right, single bond, free rotation. It can rotate. Double bond, notice the 2, it's stuck unless I break the model. I'm not. It's stuck. It's frozen. Bond angle 120 degrees. Oh, I got a protractor somewhere in my office. I should. But anyways, and with that, this is important. Double bond, you have no free rotation. This affects many things, including why certain fats are good for you and other ones aren't as good for you. We'll get that later on. Now, what does this look like? Again, let me do one thing. I don't know why it didn't pop up on its own. Here's one carbonate double bond. The gold is the sp2 orbital, 3 electrons, and the blue is the p orbital. And here's how it looks on the top. And when you bring 2 carbon atoms together to form a double bond, the sigma bond are these 2 overlapping, sharing a pair of electrons, and the pi bond forms this. And there you have your 2 pair of electrons, and that's a carbon-carbon double bond. Now, these other sp2 are where you have hydrogens or other carbons attached to it. As I showed you in the model, I went over a minute, I'm sorry. The double bond is trigonal planar, and I'll come back to this. All right, it's time to take a break. Come back in 5 minutes. Let me look at my clock. That would be 1:56. I'm gonna get up and stretch, and I'll see you in 5 minutes. Do come back. Sorry about the delay. I went and checked my mail. Time to get going again. Everybody back? All right, we're talking about double bonds. And the double bond is what's called trigonal planar. Notice all the atoms are in that gray dotted plane. Ooh, that's about the heaviest geometry we'll get into in this class. I'll never ask on tests what's the shape of a double bond. Trigonal planar. Triangle, that's how they got the name trigonal, planar, in the same plane. Again, this won't be on test, but something important you should know about. See how this is a carbon here, 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 carbon here, here. I shouldn't say if this was ethylene or ethene. You have it all in a plane. You see that? It's flat like a piece of paper, all in the same plane. And that's a very important aspect of double bond. It's in the same plane, and there's no rotation around the carbon-carbon bond, double bond, unlike a carbon-carbon here and here where your carbons are, and you have free rotation on a single bond. So anyways, that's an important feature. Did I tell you how great IUPAC was in setting up their nomenclature rules? When you get the correct name, each molecule has only one IUPAC name if you do it correctly. Let's go back and do another double bond. Let's do 2 molecules. Now, because of the fact that on a double bond, you cannot have free rotation, I can show stereochemistry like this. And you can have a different molecule like this. And everybody see those 2 molecules on your screen? Thumbs up, people. Give me a thumbs up. Thank you. All right, let's name these. Let's call these for the time being. I'm going to be real creative, A and B. And once again, using the IUPAC rules, remember IUPAC, if you do it right, each molecule has its own name. So if we look at A, what do we see? Double bond. Now here, watch carefully. This carbon is bonded to this carbon, is bonded to this carbon, is bonded to that carbon. Even though it's not in a straight line, remember, bonded, longest chain, they're linked together by bonds. Right here, these bonds and this bond. So it's 1, 2, 3, 4. What's that? Butane. What's a double bond? Drop the ANE, add ENE, butene. Now, if we start from either side, one of these carbons is going to be 2, and the other is going to be 3. If we start the other way, 1, 2, 3. So which of those 2 carbons has the lower number? And the answer is 2. So that's 2-butene. And that's how you would do A. Let's look at B. How many carbons are in the longest chain? I'll let you figure that out. And the answer is 4. 1, 2, 3, 4. Even though I'm showing what's called stereochemistry, bond angles, carbon 1 is bonded to carbon 2, which is bonded to carbon 3, which is bonded to carbon 4. They're all linked together. Oh, 4 carbons, I know that. Butane. Now, drop the ane ending. It's a double bond. Remember, we use ene ending, so that's butene. And what's the carbon of the double bond, either one, that's close to the end? What number does it have? Uh-oh, that would be 2-butane. IUPAC, you can't have A and B are different molecules. They are. You can't have the same name. Oh no, what do I do? Relax, IUPAC came up with this solution. And that's what we call cis-trans isomerism in alkenes, double bonds. Due to the fact there's no rotation around a carbon-carbon double bond, we can have 2 different isomers. They're connected to, they have the same number of carbons, same number of hydrogens or atoms in general, but they're connected differently, and you can't convert one to the other by rotating. And there are 2 things, cis and trans. Cis means same side, and I'll show you this, for 2 of the same group or carbon atoms on the carbon-carbon double bond, and trans is opposite side for same of the 2 groups, and I should also put atoms on the carbon-carbon double bond carbons. And this is a prefix, meaning it goes in front for the alkene nomenclature. So let's go back. If I click on the right thing. Now, here's cis and trans. And notice here, if I had a plane going like this, or if you put a pencil down your finger on that molecule, notice the 2 hydrogens are 1 of each on each carbon of the double bond, and they're on the same side below. Or I could have said the methyl groups, CH3, even though those are not truly methyl groups because that's not part of the name, are on the same side. So A is really cis 2-butane. Now, if we look at B, and I put in that same plane, because remember the molecule is flat and the plane goes like this, notice the hydrogens are on opposite side, opposite trans. And this you should know how to do. Hint. So this A is cis-2-butane and B is trans-2-butane. They're different molecules, and now they have different names. And like I said, and I really mean this, IUPAC did such an amazing job that no 2 molecules that are different, when you do it correctly, have the same IUPAC name. Ooh, cis and trans. Why do I think that sounds familiar? How many of you have heard of trans fats are bad for you and cis fats are better for you? You heard about that? Give me a thumbs up if you have. Well, some of you have. Well, anyways, more of you have. And what they're talking about, and we'll talk about this later on, we get the fats and oils. In unsaturated fats and oils, there's a double bond. And if the hydrogens are on the same side below, that's cis. If they're opposite, that's trans. And medical science, and I have no idea why, what's the reason? I'm an organic chemist, not a medical doctor, but they have found that the cis unsaturated fats are healthier for you, healthier than the trans. And because of various reasons, big company like Not that I get any kickback from them, and I haven't even been to one in about, well, it's been a good 20 years. McDonald's uses the cis fat now, and it costs them more money to fry their French fries in. And other companies have been for a long time, make products, and if you look on the label, it will say 0 trans fats. And they're talking about organic chemistry. So next time you're in a supermarket with a friend, neighbor, or loved one, and you pick up something that says 0 trans fat, you can tell them about how the hydrogens are not on the same side. Don't do that. People don't like hearing organic chemistry in supermarkets. All right, let's do another example. And that's one other thing I should mention. If you have two of the same group on the same carbon of a double bond, you can't have cis or trans isomerism. And this is the reason why I started out with my examples being on carbon 1, because I didn't want to have to talk about cis or trans yet. But if I look at the first example I showed you, and now I show you the stereochemistry of the double bond, notice here's my plane that's orthogonal. And notice I have a hydrogen that's opposite, but I have the same hydrogen here that's on the same side. So is that cis or trans? It's neither. So whenever you have two of the same atom or group on one carbon of the double bond, you cannot have cis-trans isomerism. But it plays an important role in our life, and the stereochemistry of double bonds even affect things in your body, such as your hormones, and also some of your proteins. But we'll get into that later on. Let's do another molecule. And let's name this. And I'll do this, and then I'm going to let you try one on your own. And so, first of all, what's different? What's not a carbon-carbon single bond or a carbon or hydrogen atom? We've got a double bond, alkene. How many carbons in the longest chain? 1, 2, 3, 4, 5, 6, 7, 8. Well, that's octane, 8 carbons. It's a double bond, drop the A on the ending, put in E, octane. Now, which carbon of the double bond is close to the end of the chain? If I go the other way, look out, I'm going Technicolor on you. Oh, I just did a generation gap. When I was in, about 6 or 7, maybe a little earlier, movies finally started coming out in color. And to advertise there in color, they always said, and new in Technicolor. Now, if we start from this side, the lead carbon close to the end is 3. If we start from this side, it's 5, which is the smallest number, and time's up. Hopefully you all pick 3. So it's 3 octane. But notice on each carbon of the double bond, I have a hydrogen. And notice they're on the same side below that dotted line. And cis is same side, and trans is opposite side. So that would be, guess what? Cis 2-octene. And let me go through that again. You see the double bond, find the longest chain with both carbons of the double bond. That was 8. And now which carbon, then that's octane, drop the A on the ending, then put in ENE, octene, and then what carbon a double bond is close to the end of the chain. And notice this carbon is at 3, the other one would be at 5. So 3 octane and 2 hydrogens are on the same side as dotted line or plane, and that's cis. This is same, trans is opposite. Your turn. What would be the IUPAC name for that molecule? It looks like everybody's just about done. I'll give you a few more seconds to finish up. And let's get going. By the way, I noticed a lot of you are watching the YouTube video from the last class, and I'll be posting this one later today or early tomorrow, and I'm about to sneeze. I think I stifled the sneeze. But anyways, I hope that helps you. All right, what do we see that's different? Double bond. How many carbons along this chain? 1, 2, 3. Remember, even though it's written not in a straight line, this carbon 3 is bonded to 4, 5, 6. If that was an alkane, that would be hexane. Drop the A on the ending, put in ENE, because it's a double bond. And now this is carbon 2. If I went the other way, it'd be 1, 2, 3, 4. Which is smaller, 2 or 4? Hopefully I'll pick 2. And now notice on the 2 carbons of double bond, I have hydrogens. They're opposite side. And remember, it even says it right here. Cis is same side, trans is opposite. And therefore, this would be trans 2-hexene. And let's do one more. And why don't you give the IUPAC name for this molecule? not counting the methyl group. Oh, I gave it away. They're 10 carbons. Now we're getting to some pretty molecules. Now you know I'm an organic chemist. All right, I think everybody's done. I'll give you another 8.2 seconds. 8.1, 8.2. All right, let's do this. Look at a molecule, look for what's different. What's not a carbon-carbon single bond or a carbon or hydrogen atom should get your attention like that. And we have a double bond. How many carbons in the longest chain? 1, 2, 3, 4, 5, 6, 7. This would be 8, but if I keep on going this way, 8, 9, 10. So the longest chain is 10 carbons. 10 carbons is decane. But it's a double bond. Drop the A on the ending and put in E on the ending. Decane. Which carbon is this is on carbon 4. If I go the other way, 1, 2, 3, 4, 5, 6. So the closest carbon with the lowest number to the end of the chain is 4. Next, notice I have a hydrogen on each carbon, and they're on the same side of this dotted line, and that's cis. And then, oh, look, I have a methyl group, CH3 is methyl group, and it's on carbon 7. So this would be 7-methyl cis-4-decene. Say that 5 times quickly. No, you don't have to. And aren't you glad I will not be doing any enunciation quizzes ever? Oh, let's do another quick one. And this one you don't have to write down. But does everybody know what that is on the screen right now? Right here? It's transparent. All right, you can all groan. Transparent hydrogens, opposite transparent, never mind. I'm gonna have to work on chemistry jokes with you people. All right. Now, there are 2 skills when it comes to nomenclature. One's here's the structure, give the IUPAC name. The other is here's the name, draw the structure. That's not what I want. I keep on always wanting to draw structures. All right, so the question would be draw 4-methyl cis-2-pentene. Let me do this one, then I'll let you have some fun. And how do you decode this? Know what to draw. You start from the right and move left. Double bond, E on the ending tells you there's a double bond. If that were ANE, that's heptane, 7 carbons. Where's the double bond? Starting at carbon 2, and it's cis. So I have carbon 1, then I have my bond angle, and cis means the hydrogens for this class, the other things are on the same side. Was 3, 4, 5, 6, 7. Then I have a methyl group on carbon 4. 1, 2, 3, 4. And I know there are 4 bonds to carbon, so I can put in my hydrogens. So let me do that again. You start from the right and move left. You have cis-2-heptene. E on the ending tells you a double bond. If we're ANE, heptane, you should know that's 7 carbons. And the double bond starts at carbon 2, and it's a cis bond. So I have 1, 2, 3, 4. Remember, the bond angle of a double bond looks like this. So I have that. I draw in the rest of my carbons. And carbon 4, I have a methyl group. Why don't you try this one? Draw the structure for trans 2-nonene, 3.Z. All right, I think everybody's done. How do you decode this? It's the one disadvantage of being on Zoom and everybody doesn't have their webcam on. I can't tell when you're done. In a classroom, I can't. All right, start from the right and move left. E on the ending, double bond. that were ANE, nonane, 9 carbons. Where's the double bond? Starts at carbon 3. So I'll go 1, 2, then I have my double bond, and notice it's trans. That tells me the hydrogens are on the opposite side. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I know there are 4 bonds to carbon. And I put in my hydrogens. Oh, let's do one more. And why don't you try 4-tert-butyl, or T-butyl, as I'll start calling it later in the week or next week. So I'm a lazy organic chemist when we do that. Cis-2-decene. And of all the nomenclature, this is probably some of, besides the initial introduction I gave you last week, this is probably the longest I'll spend on nomenclature for a functional group, but later on they get simpler. If you want, if you're done, give me a thumbs up before I do a poll, or I can do the poll. I'll do the poll. It looks like everybody's just about done. So how do you decode this? You start from the right and go left. And now we have EN the ending. That means we have a double bond. And if that were ANE, that would be decane, 10 carbons. Where's the double bond? Starting at carbon 2, and it's cis. 1. My double bond looks like this. Cis means the hydrogens are the same side. I've just done that. That's 3, 4, 5, 6, 7, 8, 9, 10. Now, a tert-butyl group, and I'll show you what that looks like, you should learn that, is on carbon 4. 1, 2, 3, 4. And now I know there are 4 bonds to carbon. And that's how you do it. 4-tert-butyl, cis-2-decene. And that's how you do it. Now, one of the things I don't have a slide for, because this is easier for me to show you, is for in a ring. And if you look at what I just showed there, you can see a ring and look for what's different. Two lines between two bends of a line shows you this has a double bond. Now, it turns out, and I'm not sure the exact number of carbons you need because of the bond geometry, but you need a lot of carbons in a ring, a big ring, to have a trans double bond. When you have a small ring like 4, 5, or 6 carbons, even 7, I think 8 too, you can't have a trans double bond. So first of all, the ring serves as the base name, cyclohexane, but there's a double bond. Double bond has the ene ending. And everybody knows when the double bond is the only functional group in a ring, which in this class I will have that way, one of the carbons of the double bond always has to be number 1, and you don't name it. And it's always going to be cis, which this is. I'm going to show you the hydrogens. I normally wouldn't draw that in. That's cis. So I'm done. This is cyclohexene. Again, ring 6 carbons, cyclohexane, drop the ane, put in ene, cyclohexene. One of the carbons has to be 1, the other 2, everybody knows that, so we don't put a number. And this is always going to be cis in smaller rings we deal with in our daily life, and we won't do that. Now, let me show you something that's a little confusing, but if we look at this molecule, I have now a ring with a double bond, and it's got a methyl group on it. CH3 is methyl group. So it's 6-membered ring, cyclohexane, but it's a double bond, cyclohexene. Now I don't put 1 or cis because everybody knows one of these carbons has to be 1 and the other is 2, the number 2. Now I have CH3, and that's a methyl group. Now here's the hard part. But once you practice, it's not. One of the carbons of double bond has to be 1, the other is 2. And you number it in such a way that one of the carbons is 1 and 1 is 2, and the other alkyl groups on a ring have the lowest number. Well, if I call this 1, this will have to be 2, this is 3. And here's where students get confused. If I call this 1, this carbon now, not 2, but 1, this is 2, this is 3, this is 4, this is 5, this is now 6. You can't call this 1 and make the methyl group 2, because one of the carbons of a double bond in a ring has to be 1, the other has to be 2. Now, which is a smaller number, 3 or 6? And hopefully you all pick 3, and that would be 3-methyl cyclohexene. And why don't you try this one? What would be the IUPAC name for that molecule? And let's see if you're done. It looks like you guys are getting the hang of it. Let's do this. Look for a molecule. What's different? What's not a carbon-carbon single bond? Carbon hydrogen, a double bond. Two lines between these two carbons, double bond. How many carbons in a ring? Count every bend. There's 5. It's a ring. Don't forget the cyclo. I forgot to mention it up here. That's a common mistake in test 1. Students forget that. 5-carbon ring is cyclopentane. Drop the ANE, put ENE. One of these carbons has to be 1, the other is 2. So 1, 2, 3, or 1, 2, 3, 4, 5. Which is smaller? Hopefully I'll pick 3. CH3 is a methyl group. And it's on carbon 3. Oh, let's do one more. And there we have one for you to try now. Remember, one of the carbons is number 1. The other is always number 2 in a double bond in a ring. And you don't put cis-trans, because in the rings I always have dealt with, and you too, they'll always be cis, and everybody knows that. This one's a little challenging, but let's see. I think you're up to it. All right, looks like everybody's done. Let's do this. What do we have? A double bond. It's in a ring, 6-membered ring, cyclohexane. Drop the ANE, put ENE, cyclohexene. One of these has to be 1, and the other has to be 2. The carbons are a double bond. And notice I have an ethyl group and a methyl group. And here, there's 2 ways you could write it, even though I will do the correct one. The ethyl group is on carbon 4. The methyl group is on carbon 1. Now, if you put 1-methyl-4-ethyl cyclohexene, I would mark it correct, even though IUPAC would arrest me if I didn't. No, they won't. But anyways, that's because I'm not holding you to the alphabetical rule that E comes before M, and that's how you do it. Now, there are 2 ways, and remember, I haven't said this in a while, there's no such thing as a dumb question in my class, in my world, and therefore, if you have a question, always feel free to ask. You either use chat or turn on your mic. All right, let's look at the following. And the question is, how do you draw the following molecule? 4-isopropyl cyclohexene. Well, how do you decode this to know what to draw? You start at the right and move left. E on the ending, double bond. That were A&E cyclohexane, 6-membered ring. Now, it doesn't matter which 2 carbons you put the double bond in, most of you are going to do this. One of the carbons is 1, the other is 2. Therefore, this is 3, this is 4. I have an isopropyl group on carbon 4. That's 3 carbons, and the center carbon is bonded to the ring. Now, you could also draw your isopropyl group, and I do them both ways. You could either even put that CH3 group on the right. I don't think I ever do that though, but that would be correct. And that's how you do it. Again, go from the right, move left, double bond. E on the ending. If that were A&E cyclohexane, 6-membered ring, there's a double bond between 2 of the carbons. One of those carbons has to be 1, the other 2. And then on carbon 4, this is 1, 2, 3, 4. You can either go clockwise or counterclockwise. I could have put that 1, 2. And all you're doing, if you do it that way, is rotating. One of the things, let me remind you that I'm going to try most of the time, draw the structure how you see it. But don't forget, if I said, oh, look what I have here, and I said, quick, close your eyes. While your eyes were closed, I did this and said, oh, look, it's something different. No, you just rotate your hand 90 degrees. Don't forget, like my hand or this pencil, that's not a pencil, my stylus, molecules move around in 3 dimensions, just like we do. And if I look, I did it again. I'm sorry. Let's take a break. Come back in 5 minutes, and that would be 2:51, and I'll continue on. It's time to get started again. Time to get started. What I'm going to do, well, I see a question. Oh, okay. It's time to get started. Now, I'm going to wait until we go through some of the chemistry of double bonds. Then we'll come back and do nomenclature of triple bonds. And this just makes more sense. So let's get into the fun part of organic chemistry. And it's not nomenclature. Nomenclature is very important, but the fun part is reactions and how to make new things, which is why I'm a synthetic organic chemist, because I thought, and I still do, it's fun to do. I still do consulting in that area, besides teaching it. All right, let's talk about reactions of double bonds. Now, double bonds have a double bond here, and let me explain what I have written on this slide here. I think you're all familiar with, and don't get scared, we're not going to do any. In math, you have variables, x and y equals 10. That means in this case, x could be any number, y could be any number. And if x were 4, then you'd know y equals 6 for this to be true. I could also say x equals 2, and therefore, by the way, the 3 dots is in math, and also for logic, therefore, y equals 8. And I can keep on going. X and y are variables. In organic chemistry, and I've spent one Saturday for an hour or so, and I couldn't find it. If you ever find it, let me know. But I think I know the reason. Someone came up with the variable, if I can spell it, for organic, R. And R means that's something that has carbon hydrogens. 1, 5, 1,000, 1,000,000, a ring. Those are just variables, just like X and Y. So if I wanted to show a general double bond, I could just do it like this, or in my slides, in this case, it's cis, it could be trans. This R means there's something with carbons in there. It could be also a hydrogen. And therefore, that means any molecule with a double bond. Now, more likely than not, I'm going to rewrite it on the slide like this. Now, let me remind you, double bond, 1 pi bond, 1 sigma bond. And they're not the same. Pi bonds, I can break like that. Ooh, my finger doesn't want to do as loud. I have to fix them. New battery. Sigma bonds, you never break almost. Again, in a double bond, you break the pi bond real easy. It's fun to break pi bonds, and it's quick too. So the first type of reaction, I'm going to talk about 2 different types, is called an addition reaction, where you add things to a double bond. And if I have a double bond here and my software didn't put it into carbons, I will. And R means I could have CH3 there, I could have 5 carbons. Same thing here, I could have a hydrogen or whatever. Whenever you see a double bond, and this you don't have to write down. If I add something to it, AB, I break the pi bond, and 1 carbon of double bond gets A, the other gets B. And that's called an addition. And you've made 2 new bonds right here. And that's a very important reaction. Now, I will never ask you on a test what's an addition reaction, but I will do the following. And remember, in this class, carbon-carbon single bonds, also known as sigma bonds, are almost never broken. Now, I used to teach reaction double bonds with ozone, O3. I don't anymore. So really, except for combustion, which we did in chapter 1, you're not going to break a carbon-carbon single bond. So what that tells me is, do you break carbon-carbon single bonds? No, you don't. Remember that. Remember, there are 4 bonds to carbon, and you don't break carbon-carbon single bonds. Let's get into our very first reaction. And that's called hydrogenation. I will use the names of key reactions. I will never, ask you on a test, what's the name of that reaction? Again, I will never ask you what's hydrogenation, but I'll expect you to know it. Now, I have it one way here on the slide. A little better way will be the following. If I take any double bond and react it with hydrogen gas, H2, and I need a catalyst. A catalyst is something that makes a reaction go quicker, but it's not consumed in the reaction. And for this hydrogenation, the catalysts are either nickel metal, platinum, or palladium. Now, there's a catalytic converter that does another type of catalytic reaction in your car that use platinum or palladium. And those are very expensive metals. In the real world, in industry, we use nickel. If you're in pharmaceutical and research at a university, use platinum or palladium. And what happens is you break the pi bond. Notice there are no longer 2 lines, and each carbon of the double bond gets a hydrogen. And this is hydrogenation. By the way, the first company and the last company I worked for, we did hydrogenations. I actually would go to a plant for new reactions of new molecules and supervise it to make sure they did it right. So I've done hydrogenations anywhere from 1 pound up to 40,000 pounds. Now, since I've worked in the real world, the chemical industry, quick thing that will never be on a test, just to give you a scale of chemicals. How many of you have ever seen the vehicle that delivers gasoline to a gas station? Oh, probably all of you. Those are called tank wagons, because in the old days, they put a tank, not that big, on the back of a wagon, and that was pulled by horses. I actually saw one of those live in Germany at a celebration where they had horses doing that. But anyways, those are standardized, 40,000 pounds, 5,000 gallons. And I'm talking about, I've done a reaction hydrogenation up to that scale. I've done more. So this is a general reaction. This is like the map you would use your GPS to get from here, wherever you are in Northern Illinois, Elgin, or surrounding suburbs, to go to some city in the United States by car. You would need a map if you've never been to that city before, or use your GPS in your car. So the following you will see on my test, an important thing. Now, before we do one of these, let me mention something that's standard. I think I might have mentioned already, but I'll do it again. in chemistry, this is a chemical reaction. A plus B makes C. Now, in academics, A and B are called the reactants. They'll never ask you on the test. But in industry, which I've worked in most of my life, and I'll probably use it more often than not, these are called the starting materials. They'll never ask you that on test. Now, at the head of the arrow, C, both places call that the product or products. The organic chemists are lazy, and sometimes we'll write this reaction like this. And we put one of the products above or below, which is what I did, or one of the reactants above or below, which is what I did there. So I want you to be aware of that. That's standard. So let's look at the following. And the question would be, give the organic reaction, the organic product or products to the following reaction. And what do I do? Because I want those 3 points because I want to get a good grade in here. We established that. I don't think anybody's going to become an organic chemist. Not that there's anything wrong with that, but I already know you wouldn't be taking this if you were going to be taking become an organic chemist. So how do we do this? You look at the reactants and you say, what's different? Here I have an organic molecule. You look for what's different. What's that? A carbon-carbon single bond, carbon or hydrogen, double bond. What am I reacting with? Well, I look here and here. Hydrogen gas and platinum is a catalyst. I know catalysts for this reaction can be nickel, palladium, or platinum, doesn't matter. And what happens, you break one of the pi bond, and each carbon of the double bond gets a hydrogen. Do you break carbon-carbon single bonds? No. Therefore, I have 3 carbons here. I better end up with 3 carbons. And here are my 2 carbons of the double bond. Notice the second line I didn't write because I broke the pi bond. And each one of those carbons, my general reaction tells me, gets a hydrogen. So I'm going to do that. I know there are 4 bonds to carbon, so I can do my math. And I write it there, and there's my product. Now, watch closely. I can also write it CH3. There's how many hydrogens? 2 on that carbon. And here I have 2 plus 1. Now, the way I grade tests, oh, by the way, did I tell you I'm the person who grades my tests because I'm that close to the grader? It's me. You can write it either way, this way or this way. This way is one less step for you, and it's easier. I don't know about you, but anytime I can make my life easier on a test, I'm happy. So you can write it either way. And remember, these are the building blocks to being able to do this to make molecules in our daily life. And that's how you do it. Let me do another one. Now, one thing, and I do this on the board in a classroom, if I'm running out of space, I'll do an arrow like this. I'll do this one, then I'll let you try one. Now, the question is, give the organic product or products for the following reaction, 3 points each. Well, what do? I look at a molecule and say, what's different? What's that, a carbon-carbon single bond or carbon or hydrogen atom, a double bond. And as soon as I see that and there's nothing else different in the molecule, in my mind, all it sees is a double bond. What am I reacting it with? And I look here and here, hydrogen, and nickel is a catalyst. Remember, the catalyst can be nickel, platinum, or palladium. And I break the pi bond, and each carbon of the double bond gets a hydrogen. Now, do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5 across, plus that methyl. 1, 2, 3, 4, 5 across. Remember, the methyl group is on that specific carbon. Here are my 2 carbons of double bond. I broke the pi bond, because that's what happens. And each carbon gets a hydrogen. And now I know there are 4 bonds to carbon. And I'm done. Now, if you wanted to write this one as CH2 and this is CH2, you can. Don't. It's extra work. And that's how you use this reaction. Now, listen carefully. Notice on each example, I wrote, and this is called the general reaction underneath. Some of my best students I've ever had in 170, if you look at their test, every one of their reaction problems like this, they write the general reaction underneath. Also, some of my best students I've ever had in Chem 170, if you look at their test, they don't write the general reaction underneath. You can do it either way, as long as what I'm looking for is the correct answer. Now, I personally, in my head, this pops up, and also those who got good grades without writing it, they memorize this too. Now, how do you memorize this? Well, you write it down and say it 5 times and do it a second time. So double bond, hydrogen catalyst, break the pi bond. Each carbon gets a double bond. Notice I lost one of the lines. And the catalyst could be nickel, platinum, or palladium. Now, I will always write a general reaction when I do a specific example, because that helps you learn it better. Remember, these general reactions are the reactions that help you determine how to get from point A to point B. How many of you ever heard of hydrogenated fats and oils, which are not good for you, but they're used in products you buy? And I'll teach you later on, you take an oil like vegetable oil, you add hydrogen and catalyst, and you make the hydrogenated fats or oils. All right, I better let you have some fun too. Your turn, give the organic. What I mean by give is draw the organic product or products for the following reaction. You're doing organic chemistry, the fun part. And remember, do you break carbon-carbon single bonds? No. All right, I think everybody's done. Let's do it. Now, you look at the molecule and you're going to be sick of me saying this, but it's true every time. Look for what's different, what's not a carbon-carbon single bond or carbon or hydrogen atom, double bond. Nothing else in the molecule is different, just carbon and hydrogen. That's not going to do anything. It just comes along for the ride. I'm reacting it with hydrogen, and what's palladium? A catalyst. Remember, the catalyst can be nickel, palladium, or platinum. You break the pi bond. So remember, there's a pi bond here and a sigma or single bond. You don't break carbon-carbon single bonds, sigma bonds, pi bonds you break real easy. And each carbon of the double bond gets a hydrogen. Now, do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4. I better end up with 1, 2, 3, 4. Here are my 2 carbons of the double bond. And notice there's only 1 line between those carbons, not 2, because I broke the pi bond. And each one, my general reaction shows me, gets a hydrogen. And now I know there are 4 bonds to carbon. And you could have made that CH2, CH3, you don't have to, and I'm done. And that's how you do it. See, organic chemistry is not that hard. The key is to look for what's different, because that's where the place where the action is. Now, let's talk about rings. If I look at this reaction, I'll do this one. We have a double bond, and we're reacting with hydrogen, and platinum is a catalyst. Remember the catalyst? Platinum, palladium, or nickel, and you break the pi bond, but not the single or sigma bond, and each carbon gets a hydrogen. Now, do you break carbon-carbon single bonds? No. So I'm still going to have my ring. However, on a ring, you don't show hydrogens, and I'm done. How do you know that? Let's look at this carbon right here. How many bonds to it? 1, 2, 3. So that means if I were to put it there, there'd be 1 hydrogen. Same thing here. Now let's look at those 2 same carbons. And now I lost the pi bond, and this carbon right here has 2 bonds to it. 4 minus 2 is 2. So went from 1 to 2. So it did pick up a hydrogen. Same thing here. But you don't show hydrogens on a ring. So the correct answer would be that. And remember, you don't break carbon-carbon single bonds. So here's one for you to try. Give the organic product or products for the following reaction. And the answer is what? Well, let's take a look. First of all, I forgot to do the following. I apologize. And it looks like everybody's done. So now I can do it. I look at this and now look for what's different. The two lines double bond. Nothing else is different. It's just carbon-carbon single bonds, carbon-hydrogen. I'm reacting with hydrogen gas and nickel, which is a catalyst. And my catalyst can be platinum, palladium, or nickel. I break the pi bond, but not the sigma bond, single bond, because you don't break carbon-carbon single bonds, very rare. And each carbon gets a hydrogen. I've got that ring. Am I going to break that ring? No, those are carbon, but I will eliminate the double bond and the ethyl group, CH2, CH3. This is a carbon-carbon single bonds. That comes along for a ride too, and I'm done. And that's how you do organic chemistry. Now, I will tell you, if you don't know these, you're lost. And it will be not pleasant to take my test. If you know those, it will be pleasant and students get good grades. So you have to start memorizing that. And yes, there's a lot of memorization in organic chemistry. Now, a couple of years ago, about 5 or 6, I forgot how many exactly, one of the Chem 170 students took the time at the end of the semester to count. I think her count was, there was something about 52 general reactions. I will teach you the whole semester, not this week. Oh, that would be frightening. But anyways, I personally know about 400 or 500 general reactions. I've cut it down to the very important ones that I'll be teaching you. Those are the tools people like me use to make things, like your soap, like your fabric softener, like the plastic in this bottle, all sorts of things in our daily life. And Mother Nature uses them too. So they are important. So that's hydrogenation. Now, we'll be coming back to that when we talk about hydrogenated fats and oils. Well, hang on. Sorry about that. I don't know why that does that. It only happens in organic when I have a lot of structures, which probably take up a lot of memory, even though I've got a lot on this machine. All right, let's continue on. Now, this is hydrogenation. We just went through. Let's talk about halogenation. Now, hopefully, all remember the second to last column of the periodic table is called the halogens: fluorine, chlorine, bromine, and iodine. Now, organic chemistry, I don't know why, has the variable X equals fluorine, chlorine, bromine, or iodine, the halogens. And halogenation is the addition of halogen gas, X2, to a double bond. And here's the general reaction, and let me write it a better way. I take a double bond and react it with halogen gas. Here you don't need a catalyst. I'll remember X here is fluorine, chlorine, bromine, or iodine. I break the pi bond. Remember, double bond has one pi bond, which you can break real easy, and a sigma bond. And here, each atom of the double bond carbon atom gets a halogen bonded to it. And that's halogenation. Again, you break the pi bond, and each carbon of the double bond gets a halogen. Remember, X is fluorine, chlorine, bromine, or iodine. And if we look at the following reaction that I'll do, and I'll let you try one in a second. If you have a double bond, what's different in this molecule if you were asked to give the reaction product or products? Double bond, halogen gas, I'll just call it halogen, and we use X for that. Remember, X can be fluorine, chlorine, bromine, or iodine, the halogens, and you break the pi bond, and one carbon gets the X and the other gets the X, halogen. So do you break carbon-carbon single bonds? No. So I have 1, 2, 3 across. I'll have 3 across. Which 2 carbons have the double bond carbons? Those which are these 2. Do you have to put dots and things like that when you do your answer? No. This way, you're saying what to look at. In the classroom, I do the same thing. And each one gets a halogen. What's my halogen? Bromine. And this counts as a single bond to carbon. I know there's 4 bonds to carbon, if I can count. And that's one way of drawing it. Now, another way, which I don't encourage, but you can, would be like this. The top one is easier for you to do. Now, let's say you were, let's say you were taking anatomy and physiology, which some of you who are going into nursing or have taken or will take. And I'm asked to draw, and I've never taken A and P, so I'm just picking on it. If you were asked to draw the hand and you put the thumb over here next to the pinky, they still call it a pinky, don't they? As opposed to next to the index finger, is that the right picture of your hand? No. Well, guess what? Where you put atoms in a molecule make a difference. Sometimes it can be a difference between life and death. I'll talk about an example later in the semester, how a company messed up big time. So let's look at another example. And this shows you the importance of where you put things. And if we look at the following reaction, which I will do, what's different? What's not a carbon-carbon single bond, carbon or hydrogen, and we have a double bond. What are we reacting with? Halogen gas. Iodine is a halogen. Remember, the halogens are fluorine, chlorine, bromine, or iodine. That's a Br. And you break the pi bond, not the sigma, single bond, and each carbon of the double bond gets a halogen. Now I have 1, 2, 3, 4 carbons across, and you don't break carbon-carbon single bonds. Never. No, it's rare. So I have 4 carbons. Which were my 2 carbons of the double bond? These 2. And what's my halogen? Iodine. I'll put in my hydrogens. And that's the correct answer. Now watch closely because it's important. And students always argue. If you were to write this in red, that's wrong. You can't get it. The iodines go to the 2 carbons of the double bond, these 2 carbons, which are these 2. So that's important to remember that. Where you put atoms in organic chemistry make a big difference, right or wrong difference. That's Cl2. What would be the organic product or products for a following reaction? By the way, one of the things I've been training you today, and well, the whole semester, is when you look at a molecule, look for what's different. What's not a carbon-carbon single bond or carbon hydrogen should get your attention like that. Or like this. And it should. And please be patient. I try and give everybody time to finish. Remember, if you have any questions or need any help, I have my office hour today from 5 to 6:15. Same thing on Wednesday, different Zoom login. All right, I think everybody's done. Let's take a look at this problem, this reaction. And the question is, what's the organic product or products? And you look for what's different. Ooh, a double bond. The rest, they're just going to come along for the ride. I'm reacting it with chlorine gas. Remember, halogen is X, that's X2. The halogens can be fluorine, chlorine, bromine, or iodine. And you break the pi bond, and each carbon of the double bond, oops, my mind was on the last problem, gets a halogen. Remember, stands for either fluorine, chlorine, bromine, or iodine. Do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5, 6 across. I better end up with 6 across, or you're not going to get any credit. Which two carbons are the carbons double bond? These two, but I broke the pi bond. Each one gets a halogen. In this case, it's chlorine. And I know there are 4 bonds to carbon. And there you go. And that's how you make that molecule. Oh, let's do one more. And the question is, if you react that molecule with fluorine gas, F2, what would be the product or products for the following? And for those who are finished, I like to make sure everybody's finished. I'll give you a few more seconds. Finish. All right, looks like everybody's done. Now, what I've done here is the chemistry instructor's favorite trick on a test. Put a big, scary molecule. But if you know where to look and what to look at, it's not a big, scary molecule. If you don't, you look at that and you go, eek. Hopefully you never do eek on my test. And here, what's different? What's not a carbon-carbon single bond, carbon or hydrogen? And the answer is a double bond. All the rest comes along for the ride. So I have a double bond. I'm reacting it with a halogen. X can be, in this case, it is fluorine, chlorine, bromine, or iodine. You break the pi bond, not the sigma or single bond, and each carbon of the double bond gets a halogen. So if I look at this molecule up here, I have 1, 2, 3, 4, 5 across. Here are my 2 carbons double bond, but I also have these 4 methyl groups that I better put in. I break the pi bond. Each of those two carbons right here gets a halogen. In this case, it's fluorine. I know there are 4 bonds to carbon, and it's time for me to get to work. And I'm done, and that's it. Now, one of the questions is, why do you want to put halogens on a molecule? Well, it turns out there's certain reactions that by making a molecule with halogens, you can react it further to make other things. That's one thing. And then another thing is certain halogens like chlorine and bromine in molecules are used to make fire retardant cloth or clothing. And why is that important? Because that way you can make fire retardant clothing for children. Before they found this out, if a child got too close to a heat source like a candle, their sleepwear would go up like that in flames, and unfortunately, they would be severely injured or possibly killed. This slows down that if they do get near that, makes it less flammable. There's no molecule that can stop something that will burn from burning, but it can slow it down. That's why we call it fire retardants. Now, about 4 or 5 years ago, 4 very clever reporters from the Chicago Tribune did some investigating. They found that the chemicals, fire retardants that were put into furniture and other things like my monitor, other plastics like right here, my printer, guess what? They really didn't work. They're based on a research paper that never claimed that. But the companies that made that chemicals convinced everybody, buy our stuff, it's good stuff. And turned out when it's put into things like couches or other things like that, it gets put into the air. And a lot of chemicals that have more than one halogen, or even one halogen, are carcinogens. They give you cancer. I don't know if they've taken some products, they have taken the halogenated hydrocarbons out of the fire retardants, and I don't know how they're doing it now. And if you look at some of the laws from California, they require a warning label if they're in there. Illinois doesn't. So that's why you do it, but overall, it's an important reaction. Now, if I look at the clock, we're almost out of time. Wow, time flies when you're having fun with double bonds. All right, Wednesday, because I lost time a week ago, we started late. Normally on a Wednesday, I'd go 50 minutes. Hold on 1 second. I'd go 50 minutes, take a break, then we do our lab and you get out early. But since I've lost time, I'm going to make up some of that time Wednesday. You'll still get out, you'll get out on time. Now, let's go to Blackboard School. Let's really bear with me. I'll be going just a few seconds over. Oh no, I said I wouldn't do that. Now, thumbs up, people. Do you see D2L? If you go and click on up here, the assignment area, you'll see the first lab. And I'll go over this on Wednesday, and I'll be doing this for all the labs. Notice I have the lab as both a Word document and a PDF. And when later on, when you have to submit it, I have it where if you don't have a scanner, you can use your cell phone to scan it or take a picture and convert that into a PDF file. Then I have instructions how to upload it here. And this is due next week, always the week after the lab, we're doing it. And with that, I'm done for today. All right, I hope you had a good time. We're getting into the good stuff now. With that, remember Yiddish, gehen gesund means go in health. And I'll say, like my grandmother always said to me, Grandma Greenman, when we left after visiting her, gehen gesund. And I'll say gehen gesund to you because of the pandemic. And goodbye. I stole that from Beverly Hillbillies. Bye.
Thank you.